Hi everyone! In today's video, we're going to use molar mass in calculations. So last time we saw that molar mass tells us the relationship of 1 mole of an element or a compound with its mass in grams. So remember that molar mass conversion factors are fractions written from the molar mass, or we could also call those ratios. And they relate grams and moles of an element or compound. So for example, methane, CH4, which is used in gas stoves and gas heaters, 1 mole of methane is equal to 16.05 grams of methane. So we can turn that into different conversion factors. So for instance, if we were calculating the mass of a sample of methane, we would use this first conversion factor, where mass is in the numerator. But if we were calculating moles of methane, we would use this second conversion factor, where moles is in the numerator. So let's go over a practice problem. So let's say we have a box of table salt, sodium chloride, or NaCl, and let's say it contains 737 grams of sodium chloride. How many moles of sodium chloride are in the box? Okay, so we're given the mass of sodium chloride, at least in this box of table salt, but we need to determine how many moles of sodium chloride we have. So our plan is to convert the mass that we were given to moles, and we're going to use the molar mass in order to do that. Now, we don't know the molar mass of sodium chloride just yet, so we will have to calculate that. Okay, so let's calculate the molar mass of sodium chloride. Now, we just have 1 sodium and 1 chlorine, so I'm going to kind of skip the mole part of our calculation. I'm just going to add together the 2 molar masses from the periodic table. So the molar mass of sodium, let's go to our periodic table. Let's see, sodium is number 11. So its mass is 22.990. Okay. Grams per mole, and then we'll just add the molar mass of chlorine. So let's see, chlorine is number 17. So that has a mass of 35.453. Oh, 35.453. Okay. All right, so when we add those 2 numbers together, let's see, we get, I'm just going to use my calculator. That'll be a little quicker than trying to do it by hand. All right, so I get 58.443. Now, again, some periodic tables will only give you 4 sig figs or even just 3 sig figs for the molar mass, so don't worry too much about sig figs here. It just depends on your periodic table. All right, so now we have the molar mass of sodium chloride. So really, another way we could write this, we could say that there are 58.443 grams of sodium chloride for every 1 mole of sodium chloride. And now we can turn that into a conversion factor. Okay, so I'm just going to make some space over on the side here. So now we can set up our problem. We can say, okay, I have 737 grams of sodium chloride in this box of sodium chloride. So now how many moles is that? Okay, so we're going to set up our conversion factor. Now, do we want moles in the numerator or the denominator? So we're trying to get to moles. That's our desired unit. So we're going to put moles in the numerator. Okay. And then we'll put the other part of the equality in the denominator, which is 58.443 grams. All right, so now grams of sodium chloride will cancel. And if we simplify, we have 737 over 58.443. And our final unit is moles of NaCl. Okay, so now we just have to plug that into our calculators, unless you want to do that the long way, which would take probably forever. Okay, so my calculator tells me that we have 12.6105, etc., moles of NaCl. Okay, so now for sig figs. So the periodic table that I was using had 5 sig figs for each of the molar masses. And when I was adding those two values together, both values ended in the thousandths place. So my molar mass for sodium chloride ended in the thousandths place. But now we're performing a division problem, 737 divided by the molar mass of sodium chloride. So now we're going to look at the least amount of sig figs. So how many sig figs does 737 have? 3. And then how many sig figs does 58.443 have? 5. Okay, so that means we need to limit our final answer to 3 sig figs. So remember, we need the least amount of sig figs for multiplication and division problems. So we're going to limit our answer to those 3 digits. Okay, and it looks like the first digit we're dropping is a 1, so we don't have to round. We can just keep this the same. All right, so we have 12.6 moles of sodium chloride. All right. So not too bad. There was an extra step for this problem. We had to calculate the molar mass first before we could use it. But then once you have the molar mass of your element or your compound, you just set it up like any other dimensional analysis problem. All right. And then here are the solution slides. Let's see if we got the same answer. 12.6. Perfect. Okay, so let's do another problem. A sample of water, which remember is H2O, has a mass of 59.8 grams. How many moles of water are in the sample? So if you want to try this one on your own, you can pause the video, and when you come back, we'll do it together. All right, so this is very similar to the last problem we did together. We're given a mass of water. So maybe this water is sitting in a beaker or in a glass. And we want to figure out how many moles do we have? Okay, so our plan, again, we're going to convert the mass to moles. And we need the molar mass, which gives us that ratio of mass to moles for water. Okay, so let's calculate the molar mass of water. All right, so we have two hydrogen atoms. So I'm actually going to set this up so I have 2 moles of hydrogen times the molar mass, which in a previous lecture we saw was 1.008 grams of hydrogen for every 1 mole. And then we're going to add oxygen. So we just have 1 mole of oxygen, and we saw previously that oxygen's mass is 16 grams per mole. All right, so I'm just kind of setting this up as one long problem, but we're going to see that moles of everything cancels and we end up with grams. So we'll have 2 times 1.008, which is 2.016 grams of hydrogen, plus 16 grams of oxygen. So that will equal 18.02 grams of H2O, which also equals 1 mole of H2O. All right, so we have the molar mass of water. So now we're going to use that relationship in our next step. So let's start with what we were given. We have 59.8 grams of H2O, and we're just going to multiply that or divide that by the molar mass. But let's figure out what we have to do here. So should 1 mole of H2O go in the numerator or the denominator? So similar to our last problem, 1 mole will go in the numerator because we're trying to get to moles, right? That's our desired unit. And then we'll put the other part of our equality in the denominator because we're trying to cancel grams. Okay, so grams of H2O will cancel, and we're just dividing 59.8 by 18.02. So let's plug that into our calculators. Okay, so I get 3.3185, etc. moles of H2O. Now, how many sig figs should we have for our answer? So it looks like our first value, 59.8, has 3 sig figs, and our molar mass has 4 sig figs. And 1 mole is exact, so we're just going to ignore that when we're figuring out sig figs. All right, so it looks like 3 sig figs is the smaller amount, so we're going to limit our answer to 3 sig figs. So this is 3.3, and it looks like the first digit we're dropping is an 8, so we have to round up to 3.32 moles of H2O. Okay, so not too bad when we kind of put everything together. And here are these solution slides. Let's see if we got it right. 3.32, awesome. Okay. So to kind of summarize what we've gone over so far in this module, we started off converting between moles and atoms, or particles or ions or molecules, whatever we were counting. And we did that using Avogadro's number. Now we can also convert to mass, or we can convert between moles and mass. So if you have grams of an element, you can convert to moles of that element using molar mass. Now, if you have a compound instead of a single element, you can do the same thing. If you have grams of a compound and you want to get to moles of that compound, or vice versa, you can use the molar mass of the compound, which we just saw in our past two problems. Now we can also take that a step further and figure out how many molecules we have, or formula units, depending on if you have an ionic compound or a covalent compound. And you can do that using Avogadro's number. We also saw previously that you can convert between moles of an element and moles of a compound using subscripts. So for instance, we saw the example with aspirin, and we could convert to moles of oxygen, knowing that there are 4 moles of oxygen for every 1 mole of aspirin. And then we also took that a step further. We converted that to the number of atoms of oxygen using Avogadro's number. Now what's really cool is if you have atoms of an element, you could convert that to molecules of whatever you have, again just using formula subscripts. So just using the ratios between an element and the compound that it's in. So this is a really handy chart. I sometimes just write this as mass to moles to atoms / molecules. And then above that I write, okay, I need the molar mass to convert between mass and moles, and I need Avogadro's number. Oh, my doorbell went off, it scared me, to go between moles and atoms. So you can also go back the other way. Let's say you have atoms, so like the number of atoms in a sample. You can determine the number of moles using Avogadro's number. So you'll just kind of flip your conversion factor. Or if you have moles, you can go to mass using the molar mass. But you might have to flip the molar mass conversion factor. So you can go back and forth across this diagram just depending on what you're trying to calculate. All right. So next time we're going to talk about something called stoichiometry, which is a really fancy word for molar relationships between reactants and products. So for instance, if you have a reaction or a balanced equation like the one seen here, you can use the coefficients as ratios. So you can convert between how much of a reactant you have and how much product you expect to form, as an example. So we'll go over that next time, but make sure to reach out to me if you're struggling with these concepts. These are very important in chemistry. We use them all the time. So if you are struggling with dimensional analysis or setting up these problems, let me know. You can also reach out to the Writing and Tutoring Center or Kayla Shaffron, who's our kind of tutor for the class. But happy studying, and I will see you in the next video.